What's good? What's good? Hopping back in. So I finished linked lists, and now I'm on the quiz about linked lists. So, what is the head node in a linked list? First of all, let's clear that. What is the head node in a linked list? The first node in the list. Which of the following nodes is the head node of LL? So we have this class node, def init, self, value, next node defaults to none, self.value is value, self.next node is next node, class linked list, def init, self, head node defaults to none, self.head node equals head node. So we have A is a node with a value of 5, B is a node with a value of 70 and a next node of A. So B is the head node. C is a node of 5,675 and a next node of B. So C is the head node, and D is a node with a value of 90 and a next node of C. So D is the head node. LL equals a linked list with a head node of D. And it's saying which of the following nodes is the head node of LL? D. Fix the node class so that some node equals node 6 can run without error. So class def init self value next node, self.value equals value, self.next node equals next node, some node equals node 6. What we need to do is default next node to none. So line 2 should be def init self value next node equals none. How is a linked list terminated in Python? By a node with data to none, by a node with a pointer to none. How is a linked list terminated by a node with pointer to head? Yes, by a node with a pointer to none. What output would you expect to see in the terminal if you ran this code? Class node def init self value next node equals none, self.value equals value, self.next node equals next node, class linked list def init self head node equals none, self.head node equals head node, def stringify list self string list equals an empty string, current node equals self.head node. So the current node starts at the head node of the linked list while current node exists. So while current node string list plus equals string current node dot value plus a period, current node dot next node is assigned to current node, and then we return the string list. So what output would you expect to see in the terminal if you run this code? So similarly to the first question, right? We have that linked list from the first question, and now we're printing ll.stringify list. So I'd expect to see 90. So these just in reverse order right here. It is possible to traverse a linked list through its list property, which keeps track of each node in the list. No. Linked list only keeps track of the first node in the list. To traverse the list, it needs a method that loops through each node to find the following node. Linked lists are made up of what elements? List items, nodes, it's made up of nodes. Linked list nodes do not contain which of the following? Roots, they don't contain a root. Pointers, they do contain a pointer. Data, they do contain a data. And links, they do contain links, so they do not contain roots. Consider the linked list. A points to B, points to C. When removing B from the list, which node needs to be updated? A needs to be updated to point to C. Given this code, what would you add to complete the .add new head method? So we have this class node, def init self value next node defaults to none, self.value equals value, self.next node equals next node. This class linked list, def init self head node defaults to none, self.head node equals head node, def add new head, self new head node. What line of code goes here? So it's def add new head node, self new head node, self dot head node equals new head node. So to add a new head, we can't just assign we can't just assign a new head to the head node. We also need to make sure that the current head node is pointing to our new head node. So we would do which is strange here because we don't see the next node. We don't see a next node method defined in our node class, but assuming there is, right? Oh, no, we do. Self.next node equals none. Oh, I see. Okay, so we need to assign our current head node to make its next node this new head node. So self dot next node equals new head node. Self dot new head node dot next node equals self dot head node dot value. No. Oh wait. Yes, new head node dot next node equals self dot head node. I think so. New head node dot next node equals self dot. No. It's this. It's necessary to set the new head node's next node property equal to the current list head node. Otherwise, you lose the connection to the current head node and the rest of the linked list. What would you add to the dot remove node method to properly maintain the linked list when removing a node? Class node def init self value next node equals none. Hold on one second. What would you add to the dot remove node method to properly maintain the linked list when removing a node? So we have a class definition of node with a def init self value next node equals none, self dot value equals value, self dot next node equals next node, a class linked list, def init self head node equals none, self dot head node equals head node, def remove node, self node to remove current node equals self dot head node. So we're setting the head node to the current node. If the current node is not equal to the node to remove, then self dot head node equals current node dot next node. Okay. Else while current node exists. So I gotta say it right. So else while current node next node equals current node dot next node. So next node is current node dot next node. If next node is equal to the node to remove, what line of code goes here? So the remove node function works like this. Take self.head node, this is the current node. If the current node is not equal to the node to remove, then we're taking current node's next node and we're making that the head node, okay? So current node's next node, self.head node. Else, sorry, if current node is equal to the node to remove, right? So now this is the head node. Else, while the current node exists, so while current node next node equals current node dot next node. So now this is the next node. If next node is equal to the node to remove, then we got to make this point to this, and then we could say current node equals none. So if next node is equal to the node to remove, current node dot next node equals next node dot next node. Current node dot next node equals next node dot next node. We can remove our next node by set, and then you set current node equals to none. Else current node equals next node. And you just do this because you're not really affecting the node itself, you're affecting the current node variable. If you said self.head node equals to none, then you'd be messing up the logic. But by setting current node equals to none, you're not actually wiping out whatever node you're on. You're just setting the variable's value equal to none so that you can exit the while loop. And it's saying else current node equals next node. Otherwise, if current node's next node isn't the value you're looking to remove, then now this is the current node and you're going to rerun the logic of the while loop. So we can remove our next node by setting our current node's next node property equal to the node that follows next node. Nice. Swapping elements in a linked list. Learn how to swap two nodes in a singly linked list in Python. Since singly linked lists only have pointers from each node to its next node, swapping two nodes in the list isn't as easy as doing so in an array, where you have access to the... Sorry, I was making sure. I'm recording, right? 1, 2, 1, 2. Cool. Again, so since singly linked lists only have pointers from each node to its next node, swapping two nodes in the list isn't as easy as doing so in an array, where you have access to the indices. You not only have to find the elements, but also reset their surrounding pointers to maintain the integrity of the list. This means keeping track of the two nodes to be swapped, as well as the nodes preceding them. Given a linked list and the elements to be swapped, value 1 and value 2, we need to keep track of 4 values. Node 1, the node that matches val 1, node 1 prev, node 1's previous node. So again, given a linked list and the elements to be swapped, say we're swapping value 1 and value 2, we need to keep track of 4 values. Node 1, the node that matches val 1, node 1 previous, node 1's previous. So let's say, okay, let's make this node 1 then, I guess. So node 1, the node that matches val 1, node 1's previous node, node 2, the node that matches val 2, and node 2's previous node right here. Or I guess I don't have another. Do I have another? I don't have another one of these. But we can make this it. So I think it's saying they don't necessarily have to be sequential, right? We can be looking, I don't even have enough hands for all this, but we can be looking to swap this node and this node, and we need to be paying attention to what this node is, node 1, that's node 1. We need to be paying attention to its previous node. We need to be paying attention to node 2, and we need to be paying attention to node 2's previous node, because we're going to have to reset a bunch of pointers. Given an input of a linked list, val 1 and val 2, the general steps for doing so is as follows. 1, iterate through the list, looking for the node that matches val 1 to be swapped. So this is node 1, keeping track of the node's previous node as you iterate, node 1 prev. So 2, repeat step 1, looking for the node that matches val 2, giving you node 2 and node 2 prev. If node 1 prev is none, node 1 was the head of the list, so set the list head to node 2. So if node 1 prev is none, then node 1 was the head of the list, so set the list head to node 2. Otherwise, set node 1 prev's next node to node 2. So again, we're iterating through the list, looking for the node that matches a value. Let's say the value is 3. We're saying which node has a value of 3. Oh, wait. So okay, step 2 is repeat step 1, looking for the node that matches value 2. So now we're going through the list. Let's say we're looking for one with a value of 8. Oh, word. This node over here has a value of 8. Cool. So now we know node 1 is right here and node 2 is over here. And we're saying these values not sequentially, but in terms of the two nodes that we're looking for. So node 2 can actually be the 10th node in the linked list, for example. If node 1 previous is none, node 1 was the head of the list, so set the list head to node 2. So we're saying now node 2 is the list head, and we don't need to worry too much about, messing up the structure of the linked list, because nothing was pointing to node 1 to begin with. But node 1 is still pointing to this other node over here, which is still, let's say, if node 2 is the third one in the list, right, then the second one on the list is still pointing to node 2, but node 2 is the head of the list. So if we started the list now, it would start at node 2 and it would ignore these other 2, but this isn't where the logic ends. If node 2 previous is none, set the list head to node 1. So if node 2 had nothing before it, then that would mean that node 2 was the head. And now we're swapping and we're saying now node 1 is the head. Otherwise, set node 2 previous' next node to node 1. So I know this is getting kind of confusing here. I'm confused too, but so if neither of these or at least if node 2 wasn't the head node, right? But now node 2 is a head node, and node 1 was the head node. So what we're going to do is we're going to take node 2's previous and set its next node to node 1. Set node 1's next node to node 2's next node, and set node 2's next node to node 1's next node. So that got a little bit all over the place. I think it's time to get the sketchpad out. I had some issues with this yesterday, but we're gonna see how it goes. We will see, we shall see. So, and the issues were mostly on me. You know, I've never used this before, but let's get tropical, you know? So, outline today, let's go with orange, because I'm wearing orange. Okay. So, how do we want to do this? Let's say we have this linked list of 5 nodes floating around in node space. Okay. This is node 1. This is the head node. Well, actually, yeah, let's not call it node 1. Let's say it's the head node. And this is the structure of our linked list in node space, right? So we're iterating through the list and say, can I type? Oh, nice. Fancy text. Let's do they have Courier New? Damn it. Do they have Mono? I'm trying to be source code pro. Nice, let's go. Gotta be Cody. All right, let me type. So, goodness. How do I change the size? There we go. All right, I'll take that. I like that. So we have val 1. Let's say val 1 is 3, just to keep it what I was saying before. Let's say val 2 is 8. So get this out of here. Get out of here. Okay. Let's justify these like that so it's easier to move around. All right, that's right there, right? We're looking for the node with val 1 of 3 and a node with val 2 of 8. And let's go ahead and we can draw these. Let's switch to let's be simple. Let's just keep it on orange. It's fine. Let's say this has a value of 3 and this has a value of 8. Okay. So we're going to iterate through this list looking for the node that matches the value of val 1 to be swapped. So that's node 1, keeping track of the node's previous node as you iterate. So on our first iteration, does this has to have a value equal to 3? No, it doesn't. So we're going to say this is not it. And does it have a previous node? No. So node prev, let's do here. And again, I know I'm going slow, but just this is for understanding. It's not for speed. It's not for anything other than understanding. So I don't care how slow I go. Goodness. Okay, I'm exposing myself. Yes, I need to get on a glycolic peel. Although every time I do any type of chemical on my skin, it just like makes me red. So if anybody has any good like skincare tips, please hit me with those. Damn, I can't even get rid of it. Damn internet, damn tech. Why you want to expose me this bad, bro? Okay. How do I walk that back? Your text here. There we go. So now that I'm no longer exposed, source code. Okay, cool. So node 1 equals this, and node 1 prev is equal to this. How do I get this off here? this is, okay, select it, cool, right? And we also have this variable node2 and node2 prev. So get this pen out here. So we looked at this, we checked this, and right now this is node 1. So I don't know how to really express this, but just think about it like this. Right now this is node 1, and node 1 prevs is none. So let's go check the next one. All right, what is it linked to? Oh, it links to here. So now this is node 1. Node 1 prevs becomes this node. Okay. Does this have the value? Yes, it does match val1. So cool. So iterate through the list looking for the node that matches val1 to be swapped. We found it. Keeping track of no one's previous node as you iterate. So in our second step of our iteration, we've found this, and now we know node 1 equals, see, I don't really know how to write this, but how would you write it, I guess? Let's say, it's hard to fit, right? But let's say this is called A, this is called B, this is called C, this is called D, this is called E. And now we're going to say node 1 is B and node 1 prev is A. Now that we've done that, we're going to repeat step 1 for the node that matches val2. So now we're looking for val2. So is this val2? No, it's not. Its previous node is none. Is this node 2? Does it have val2? No, it's not. But its previous node is A. Is node C val2? Or I should say, does node C have val2? No, it doesn't. But its previous node is node B. Does node D have val2? Yes, it does. And its previous node is node C. So we're going to save those to our variables. Node 2 is D, and its previous node is C. Okay? If node 1 previous is none, node 1 was the head of the list, so set the list head to node 2. In our example, that's not the case. Otherwise, set node 1's previous next node to node 2. So set node 1 previous next node to node 2. So node 1's previous is next node. So let's think about it like this, right? Can I type? That's as big. Oh, I have to resize the box, huh? So let's space it out a little bit. Node 1 previous dot next node equals node 2. And it's just for understanding's sake, right? Right now, that means it's equal to D. So now we said node 1 previous dot next node. So this next node, so this is now, here, let me get rid of that. So since A is node 1 previous, we're setting its next node to node 2, which is D. So now A is pointing over here to D, right? If node 2 prev is none, set the link head to, that's not the case. Set the list head to node 1, that's not the case though. Otherwise, set node 2 previous next node to node 1. So we're going to come here. We are not clicking on that one, sir. Clicking on this, deleting it, deleting that. Node 2 previous C. And now we need to set node 2 previous next node to node 1. So what we're going to do is we're going to take this, we're going to say this is pointing to this node, okay? Set node 1's next node to node 2's next node. Node 2's next node is E. So these arrows are going to get a little funky right now, but That's what we're doing. So I'm clicking on this, not that one. Excuse me. Okay, clicking on that. And click over here. Get that out of here. All right. So node 1, set node 1's next node to node 2's next node. Right now, node 2's next node is E. And the way you could think about this in code is node 1 dot next node equals node 2 dot next node, right? I know I skipped some of the steps in code, but hey, I'm not a teacher. I'm just making it work, right? That's pointing here. And then set node 2's next node to node 1's next node. So node 2 is still D, and its next node is E. Set node 2's next node to node 1's next node. I don't even know how I'm going to make this work, but I'm going to make it work. Come right here. I think I missed a step. This should be pointing to C, shouldn't it? When was I supposed to set that? Because right now our list looks crazy. But this is good. This is how learning happens, right? So okay, let's think about where we went wrong. So we're iterating through the list looking for a node. Let's do it again, right? Let's do it again. And this time, let's start with code, because maybe I'm a better coder than I am a designer in this case. Let's get that out of here. So think about it like this. We have this value. We have value 1 equals 3 and value 2 equals 8. Given an input of a linked list. And let's say we have linked list equals just following sort of the logic that we had before. Linked list is okay, so let's define some nodes first, right? A is a node with a value of 2 and a next node of B. Or that's not how you do it, right? Oh, you have to define it kind of backwards. I see. So let's do, we're gonna have, we went to E. So E is a node with a value of 2. D is a node with a value of 5, and D's next node is E. A, B, C, D. C is a node with a value of, oh wait, we made D 8. Yeah. Let's say C is equal to 5, and its next node is D. And B is a node with a value of 9, and its next node is C. And A is a node with a value of, let's say, 4, and its next node is B. All right, so we have our nodes. And these values correspond to what I had drawn earlier, essentially. Except I just didn't go through the process of writing all their values out. And now we're going to make a linked list. With a head node of A. Cool. So we're given an input of a linked list, and so we're going to say def, we're swapping nodes, right? Swap nodes. All you should need to swap these nodes is a linked list and a value. Linked list, val1, and another value, val2. We're going to iterate through the list looking for the node that matches val1 to be swapped. So we're looking for a node that matches val1, which in this case was 3. And I had made B, right? Cool. Looking for this, and we're looking for this, and we're going to swap whichever nodes match these values. So we already know we're going to try to swap B and D. We iterate through the list looking for the node that matches val1 to be swapped, node 1, keeping track of the node's previous node as you iterate. Repeat step 1 looking for the node. So current node equals you know what? I'm admitting, no, I can't admit defeat. I'm not admitting defeat. I just don't want to waste my time, right? And they're about to show us a little bit better how to do this. But I have the basic concept down. So I understand what needs to be done, and I understand sort of how to set up the problem. I might just not have the best understanding of exactly how to write out this function, but we're about to find out. But we understand the logic, right? All you're doing is you're just searching for these two values, and you're going to swap them, and swapping them involves keeping track of which node was pointing to this node, which node was pointing to this other node, and then you're going to have to move the pointers around. So finding the matching and preceding nodes. Let's look at what implementing steps 1 and 2 looks like. In order to swap the two nodes, we must first find them. We also need to keep track of the nodes that precede them so that we can properly reset their pointers. We will use the node classes .getNextNode method in order to access the next node. We will start by setting node 1 equal to the head of the list. So node 1 equals, I'm going to call it linked list dot head node. We also need to keep track of the nodes that precede them. So we will start by setting node 1 equal to the head of the list and then creating a while loop that runs while node 1 isn't none. Inside the loop, we will check if node 1's value matches val1. If so, we break out of the loop as we have found the correct node. If there is no match, we update node 1 prev to be node 1 and move node 1 to its next node. So since all we can do with our input list as the start, our linked list, is know what the head node is, we set both of these nodes, node 1 and node 2, to our linked list head node. Cool. And for right now, how did I manage to screw that up? Cool. And for now, we will make node 1's previous node none, because it doesn't have one. And node 2's previous node is also none. While node 1 is not none if node 1 dot get value is equal to val1 break. So we get out of here. But if that's not the case, then node 1 prev equals node 1 and node 1 is equal to node 1 dot get next node. Cool. At the end of this, we have found our matching node and also saved its previous node, which we'll use in the next step. So fill in the code to complete the while loop that will find node 2 and node prev. Let's think about it, right? While node 2 is not none if node 2 dot get value is equal to val2, break them. And I don't know, oh, this is supposed to be a colon. But otherwise, node 2 prev equals node 2 and node 2 is equal to node 2 dot get next node. Nice. So this box right here, we're doing val2, and this we're doing break, and this we're doing node 2, and this we're doing that. Cool, cool. Updating the preceding node's pointers. Our next step is to set node 1 prev and node 2 prev's next nodes, starting with node 1 prev. We'll begin by checking if node 1 prev is none. If it is, then the node 1 is the head of the list. So if node 1 prev is none, then node 1 is the head of the list. That's just a fact. And so we will update the head to be node 2 because we're swapping them. If node 1 prev isn't none, then we set its next node to node 2. So still inside the swap nodes function, coming down here, if node 1 prev is none, in our thing it's called linked list, not input list. Linked list dot head node is node 2 now. Okay, otherwise, else node 1 prev dot set next node to node 2. Otherwise, we need to take the node that was previously pointing to node 1, which in our case is B, is node 1, and previously A was pointing to B, but now we have to make A point to node 1 previous dot set next node. Now A is going to have to point to D, which is our node 2. After this step, we have finished updating the pointers that point to our swap nodes. The next step will be to update the pointers from them. So fill in the code to update node 2's previous node. I don't know why the tabs are crazy on this. It's inconsistent. It seems like unless I'm doing something wrong. If node 2 prev is none, linked list dot head node equals, so if node 2 previous was node 1 is none, then that means that node 2 was the head node. So now we're going to make the linked list head node node 1 because we're swapping them. Else node 2 previous dot set next node to node 1. So now the node that used to point to node 2 is pointing to node 1. So if node 2 previous is none, in their case input list dot head node equals node 1. Else node 2 previous dot set next node to node 1. Updating the node's next pointers. The last step is to update the pointers from node 1 and node 2. This is relatively simple and mirrors a swapping function for an array in that we will use a temporary variable. Fill in the code to set node 1 and node 2's next nodes. Temp equals node 1. It's getting a little bit too long for this, but I'll hide some of this stuff. Make this longer. So temp is node 1 dot get next node. So the last step is to update the pointers from node 1 and node 2. This is relatively simple and mirrors a swapping function for an array, and then we will use a temporary variable. So we take node 1's next node and we store that in this temp variable. And then node 1 dot set next node to node 2's next node. So node 2 dot get next node, and then node 2 dot set next node is going to be equal to our temporary variable. Edge cases. We've completed the basic swap algorithm in Python. However, we haven't accounted for some edge cases. What if there is no matching node for one of the inputs? The current swap nodes function will not run because we will try to access the next node of a node that is none. Remember that our initial while loop only breaks if the matching node is found. Otherwise, it runs until the node is none. Thankfully, this has a quick fix. We can put in an if that checks if either node 1 or node 2 is none. If they are, we can print a statement that explains a match was not found and return to end the method. We can put this right after the while loops that iterate through the list to find the matching nodes. So if node 1 is none or node 2 is none, print swap not possible, one or more element is not in the list. And again, this has a quick fix. We can put an if that checks if either node 1 or node 2 is none. If they are, we can print a statement that explains a match was not found and return to end the method. We can put this right after the while loops that iterate through the list to find the matching nodes. So right in here, if node 1 is none or node 2 is none, print swap. I'm just gonna do can't swap element not here, and we're gonna do return. The last edge case, and we'll call this edge case node we're looking for missing. The last edge case is if the node, if the two nodes to be swapped are the same. While our current implementation will run without error, there's no point in executing the whole function if it isn't necessary. We can add a brief check at the beginning of the function that checks if the val1 is the same as val2, and then return to end the function. So, edge case nodes are the same if val1 is equal to val2, not forget my colon. See, the tabs are inconsistent. I gotta get off of this thing. This is the end of me using Sketch.io. But anyway, hit tab, print, and now it's my cursor looks crazy. I'm sorry, Sketch. Whoa. All right, you get the point. I'm getting off of this thing. This is crazy. So if val1 is equal to val2, print elements are the same, no swap needed, return. The finish function. Below is the final dot swap nodes function. Run it to see how it works. Does it work with edge case inputs? So we're gonna run it. We're importing node, importing linked list, def swap nodes. Can we make this a little bit bigger? No, we can't. So this function takes in an input list, takes in val1, takes in val2. So first we print swapping val1 with val2. So we're gonna swap 9 with 5 because that's what we're inputting here, right? I'm a little bit confused as to, oh, okay. Why did it print all that though? I don't understand why I printed all that before, but okay, we're swapping 9 with 5. This is our list right now. Node 1 prev is none, node 2 prev is none. Node 1 is the input list head node, and node 2 is the input list head nodes. Right now, this is node 1 and node 2's value. If, well, sorry, the word to use, right? So this is node 1, and this is what node 2 is assigned to. It's the node that's holding this 9 right here. Now, if val1 is equal to val2, then the elements are the same, no swap needed, but that's not the case here. While node 1 is not none, which is not the case, If node 1 get value is equal to value 1, break. That's the case here, so break it. Now we're here. While node 2 is not none, and it's not, if node 2 dot get value is equal to value 2, break. But that's not the case. So node 2 prev, which is none, is equal to node 2. So now node 2 is equal to none. Node 2 equals node 2 dot get next node. So now node 2 prev is none, and this node right here is node 2. If node 1 is none, or node 2 is none, which is not the case here, then print swap not possible, one or more element is not in the list. Oh, my fault. You know what? I exited the while too soon. So we still are going through this while loop, right? So right now, node 1 is this, and node 2 is this. While node 2 is not none, if node 2 dot get value is equal to val 2, then break. But that's not the case. So node 2 prev is equal to node 2. So now this is node 2 prev, and node 2 is equal to node 2 dot get next node. So node 1, node 2 prev, node 2. While node 2 is not none, if node 2 dot get value is equal to val 2, break. That's not the case. So node 2 prev is equal to node 2, and node 2 is equal to node 2 get next node. So now node 1, just a node. This is node 2 prev, and this is node 2. Its value is not none. If node 2 dot get value is equal to val 2, that's not the case. So node 2 prev is equal to node 2. So now this is node 2 prev and node 2. But then we're going to assign node 2 to, well, node 2 dot get next node to node 2. So now this is node 2. So node 1, just a node, node 2 prev, and node 2. While node 2 is not none, if node 2 dot get value is equal to val 2, then we're good. So break, we're out of those. So we're looking at node 1, just a node, node 2 prev, node 2. If node 1 is none, or node 2 is none, but that's not the case. If node 1 prev is none, which is the case, input list dot head node is equal to node 2. So now this is the head node. If node 2 prev is none, that's not the case. Else node 2 prev dot set next node. So this is node 2 prev, right? So we're going to set this next node to node 1. Cool. Temp equals node 1 dot get next node. So this is the temp. Node 1 dot set next node. Node 2 dot get next node. So now this next node is this node. Node 2 dot set next node to temp. So now this is the 5's next node, right? LL equals linked list dot linked list for I in range 10. So this is just setting it up, but we've achieved the functionality we're looking for. So swapping 9 with 5. 5 is now at the top. 5 points to 8. 8 points to 7. 7 points to 6. 6 points to 9. 9 points to 4. 4 points to 3. 3 points to 2. 2 points to 1. And 1 points to 0. And 0 points to nothing. Cool. Cool. How long did that take? Just an hour. Slight hour. 2-pointer linked list techniques. Learn how to approach linked list problems with multiple iterator pointers. Many common singly linked list problems can be solved by iterating with 2 pointers. This is sometimes known as the runner technique. So again, learn how to approach linked list problems with multiple iterator pointers. Many common singly linked list problems can be solved by iterating with 2 pointers. This is sometimes known as the runner technique. 2 pointers moving in parallel. Consider the following problem. Create a method that returns the nth last element of a singly linked list. So if we have a singly linked list, so for example, given a linked list with the following elements, 1 points to 2, points to 3, points to 4, points to 5, return the second to last element. The answer would be element 4. In order to do this, you'll need some way of knowing how far you are from the end of the list itself. However, in a singly linked list, there's no easy way to iterate back through the list when you find the end. If you want, you can try your hand at the problem directly, or we can walk you through some approaches below. So, Remember, I'm going for mastery here. Do I have time to go for mastery? You know, I'm at linked list, right? I'm near the end of linked list. And I got all this to do. And I kind of think I might have to go through this a second time. And I have 2 weeks to my interviews. I think I got time. So let's let this sink in, right? So let's open this up and format font. I want to make it I want to make my font bigger. Let's make it rich text. And let's make it Courier New. Let's make it size 30. It's a little bit too big, right? Let's make it size 20, 24. Okay. Put that right there. Take this, put that right there. So if I was going to backtrack through a linked list, it would be something like so. You know what? No, that's not what we're gonna do. I don't have as much time as I think I have. Approaches. One thing that might first come to mind is to use a list to store representation of the linked list. One thing that might first come to mind is to use a list to store representation of the linked list, and then to obtain the nth to last element from the list. I'm taking notes though, that's what I'm gonna do. While this approach results in an easy to read implementation, it could also use up lots of memory, maintaining a dual representation of the same data. Don't take a note on that. If the linked list has 1 million nodes, we'll need 1 million pointers in a list to keep track of it. An approach like this results in an extra O of n space being allocated. This code for this approach would look like the following. So it would be def list nth last linked list n. Okay, so this function, this method or whatever, called list nth last, takes in a linked list and takes in n, which is the nth last that we're looking for. Linked list as a list is a list. Current node equals linked list dot head node, while current node linked list dot as list append current node. Current node equals current node dot next node, and so on. So we're adding all of these nodes to a list, and then we can return linked list as a list. So the length of linked list as a list minus n. So I understand you're adding everything in our linked list to a actual array, and so you're taking, it makes sense that it takes up O of n space, right? You're doubling it essentially in memory. Instead of creating an entire parallel list, we can solve this problem by using 2 pointers at different positions in the list, but moving at the same rate. As in the previous example, we will use 1 pointer to iterate through the entire list, but we'll also move a second pointer delayed n steps behind the first one. A count variable can keep track of the position of the current element in the linked list that the tail pointer is pointing to, which is initially set to 1, which is the first element's position. The pseudocode for this approach would look like the following. So again, this problem is create a method that returns the nth last element of a singly linked list. Okay, this is probably gonna be too big. That's a little too small. That's just right. I'll take that. And the pseudocode for doing this, and I'll just make a note here. Use markdown format. If we try to, okay, the issue is that there's no easy way to backtrack in our traversal of a linked list unless we intentionally store the nodes. But if we copy our linked list to an array so that we can easily assign the nth element of the array to variable, we have to double the memory of the linked list, which is bad. So instead, we use two pointers. One steps through the whole list, the other steps through with a delay of n. That way, when the first pointer makes it to the end of the list, the second pointer will be on the nth last element. Okay? Pseudocode. Nth last pointer is none. Tail pointer is linked list head count equals 1. While tail pointer exists, move tail pointer forward, increment count. If count is greater than or equal to n plus 1, if the nth last pointer is none, set nth last pointer to head. Else, move nth last pointer forward. And then return nth last pointer. So if I was going to make this in Python, so nth last, we'll do nth last pointer equals none. Tail pointer equals linked list dot head. Or we'll do linked list dot get head node. Right? So we get the linked list head node and we assign that to the tail pointer, and count equals 1. So while tail pointer, move tail pointer forward, tail pointer equals tail pointer dot get next node. Or I think we could just do dot next node. And count plus equals 1. If count is greater than or equal to, oh, and again, this is, so def move, create a method that returns the nth last element of a single list. So return nth last, which takes in a linked list and n. Cool. So if count is greater than n plus 1, if nth last pointer is none. Set nth last pointer to head. So the nth last pointer becomes equal to the head. Okay, so nth last pointer equals linked list dot get head node, else move nth last pointer forward. Nth last pointer equals nth last pointer dot get next. Or I don't need to do that. I could just do dot next node. I'm a little bit, making assumptions about the structure of what the linked list and node classes are here, but I'm basing this off the structure of what we've been learning. So I don't need that. And then when all of that is said and done, eventually the tail pointer will be set to none, because again, tail pointer equals tail pointer dot next node. Once we finally get to the end of the list, remember the last node in the list's next node is set to none. So when that finally happens, then we will exit this list, and by that point, if count is greater than or equal to n plus 1, which will always be true. Sorry, if n is, let's say we're looking for the 10th last node. So let's think about, is it going to show us an example? Okay, it will. Cool. When the tail pointer moves n nodes into the linked list from its starting position of 1, when the tail pointer moves n nodes into the linked list from its starting position of 1, it will be at position n plus 1. I see. Again, when the tail pointer moves n nodes into the linked list from its starting position of 1, it will be at position n plus 1. We want the nth last pointer to be n nodes behind, so we set the nth last pointer to the head node at position 1. This is because the position n nodes behind the n plus 1th node is n plus 1 minus n is equal to 1. Then each following iteration will move both pointers at the same speed until the tail pointer points to the end of the linked list. Let's visualize the steps of the algorithm through the following example, where we want to obtain the second to last node of the linked list. T represents the tail pointer and n represents the nth last pointer. For each iteration of the while loop, we will also keep track of the count value. Starting state, count equals 1, t, 1, 2, 3, 4, 5. On the first tick, the tail pointer is now pointing to 2. On the second tick, the tail pointer is now pointing to 3, and the count is now 3, so n is pointing to 1. On the third tick, count becomes 4, t is pointing to 4, then count becomes 4, and n is pointing to 2. And on the fourth tick, t is pointing to 5, the count is 5, and n is pointing to 3. And on the final tick, t is pointing to none, n is pointing to, or the count is 6, and n is pointing to 4. And 4 is the second to last element of the list. Implementation. Complete the nth last node function so that it returns the correct node instance or none if the linked list. So this was for studying purposes, right? So nth last node in linked list. Where am I going to save this? We'll save it to documents. Create DSA. Save it there. Close that. Full screen this. So, full screen it for real though. Complete the nth last node function so that it returns the correct node instance or none if the linked list is shorter than n elements. Do this without creating any additional new data structures such as a list. You can assume that the linked list has no cycles. You can use the generate test linked list function to test it yourself. It returns a linked list with values from 1 points to 2 points to all the way up to 49 points to 50. So from linked list, import linked list, complete this function. Def nth last node takes in a linked list and takes an n. So how would we do this, right? We need to initialize. I hate that it's so small. I can't make this bigger. Whatever. Initialize our tail pointer and our nth last pointer. So tail pointer equals linked list dot get head node and our nth last pointer equals linked list dot get head node. And again, we're initializing our tail pointer and our nth last pointer to the head node of the linked list. Initialize a counter variable to track where we are in the list. Count, we'll do counter equals 1. Then what we need to do is start stepping our tail pointer through the list and keep track of where in the list it is. So, but when the tail pointer reaches the end, this loop should break. So while tail pointer equals tail pointer dot next node and counter plus equals 1. So keep doing that. So it does that if check if we've made it far enough into the list that the distance between the tail pointer and the nth last pointer is sufficient to start stepping the nth last pointer through the list at the same rate as our tail pointer. So if the counter is, so let's say our nth last, we're looking for the 5th last. So tail pointer starts at the head, moves to the next node, counter's now 2, moves to the next node, or it keeps doing this. But what are we waiting for? We're waiting for the signal that the tail pointer is at the 4th node. Or no, it's at the 6th node. Once the tail pointer gets to the 6th node and our nth last is at the 1st node, now we can start moving them together. So if counter is greater than or equal to n plus 1, so check if we made it far enough into the list that the distance between the tail pointer and the nth last pointer is sufficient to start stepping the nth last pointer through the list at the same rate as our tail pointer. If counter is greater than or equal to n plus 1, I know this is wrong, but I'm going to figure out why it's wrong. So then we start stepping the nth last pointer at the same rate as the tail pointer. Nth last pointer equals nth last pointer dot next node. So nth last pointer equals nth last pointer dot next node. And then if we came up here and we just let that be the end of it, right, what would happen? So while the tail pointer exists, tail pointer equals tail pointer dot next node. So tail pointer moves and the counter goes up. If the counter is greater than or equal to n plus 1, then nth last pointer equals nth last pointer dot next node. And then what if we restart the loop there? Tail pointer still exists, so tail pointer equals tail pointer dot next node. Counter goes up. Counter is already greater than or equal to n plus 1. So we step, 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 step. And then eventually tail pointer will be equal to none. And our loop will be done. But there's a key element that I'm missing here, which is what? It's that if the nth last pointer is none, the nth last pointer is none, set nth last pointer to head. Oh, okay, I see. I initialized it, didn't I? I think I did this in my code too. Oh, okay. In my head, I was thinking, did I do this down here? Yeah, I did this down here. I started the tail pointer as the linked list head, which I guess could work in a way too, right? I guess the fear, I don't know. I don't know what the fear is there. But here we're checking if it's equal to none. But what would happen, let's see, if we just do what I did and we return the nth last pointer. Expected the ninth last node value to equals 42. Instead we got 48. Huh. In our def generate test linked list equals linked list for I in range 50, 0, -1. So I guess it's reverse. Oh, I see. Yeah, for I in range 50 to 0, -1 means we're going in reverse. Linked list dot insert beginning. I don't know what that means. Linked list dot insert beginning I. Oh, okay, so we're just kind of like appending it, right? Return linked list. So now our linked list has a head of 1. Okay, so yeah, you have to get like a reverse. You have to get so the range function creates an array, and what it just did right there, if we do starting at 50 ending at 0 -1, that means our array is going from 50 to 0 in descending order, and then we're taking each element of that and inserting it at the beginning, which gets us a linked list from, oh, and it's the 0 here is exclusive, so we end up with a linked list from 1 to 50 in ascending order. Use this to test your code. Test list equals generate test linked list. Okay, and then we print our test list, which is this, and they added this head and tail to show us where it starts and where it ends, and then print nth last node, which is the function I made, and we're sending it our test list and an n of 4. Print nth last value. So in this case, what I did, which seems like it was wrong, was I started the tail pointer at the head node, started the nth last pointer at the head node, and then started the counter at 1, and then started stepping through. Tail pointer exists, tail pointer is right here. So tail pointer is the next one, counter goes up, so now counter is 2. Is the counter greater than or equal to 4 plus 1? No. So just keep doing this. Now this is where the tail pointer is pointing to, and the counter is 3. Is that greater than or equal to 4 plus 1? No. So then this, is that greater? No. Is then this? Yes. That is equal to 4 plus 1. So now that that's the case, the tail pointer is here, and we're moving our nth last pointer here. And we're going to keep doing that. So move this, and then move that. So 6 and 3, 7 and 4, 8 and 5. And the idea here is that 1, 2, 3. This is, if this was the end of the list, then this would be at the third last. But if we start this at none, if we start this at none, first of all, expected the nth last, so the 9th last node value to equal 42. I thought we were testing it with 4. Either way, if we add in that little, this check here, so if nth, so let me write it in pseudocode first. If the nth, so check if the nth last is equal to none, and if so, set it to the head of our linked list. If nth last pointer is none, nth last pointer equals linked list dot head or get head node. Start stepping the nth last pointer. So else nth last pointer equals nth last pointer dot next node. And that was the only difference, right? So now if we run it, okay, makes sense. So we were just slightly off. Okay, so you have to start the nth last pointer at none. You can't start it at the head node. Makes sense. Solution. In Python, we can implement the nth last node finder function as such. Def nth last node linked list n, current equals none, tail seeker equals linked list dot head node, count equals 1, while tail seeker equals tail seeker dot get next node, count plus equals 1, if count is greater than or equal to n plus 1, if current is none, current equals linked list dot get linked list dot head node, else current equals current dot get next node, return current. The exact variable names aren't important, and the internal implementation could be written in a number of ways, but the important part is that we are able to complete this program efficiently. In O of n time, we must iterate through the entire list once, and O of 1 space complexity. We always use only 3 variables no matter what size the linked list is, 2 pointers and a counter. Pointers at different speeds. Using 2 pointers moving in parallel was a good solution to the previous problem. However, there are other problems where having 2 pointers moving in parallel wouldn't be as useful. Let's take a look at one of those problems and consider a new strategy that uses 2 pointers moving at different speeds. Consider the following problem. Create a method that returns the middle node of a linked list. For example, given the linked list with the following elements, 1 points to 2, points to 3, points to 4, points to 5, points to 6, points to 7, the middle node would be the element with value 4. And again, the problem we're doing is creating a method that returns the middle node of a linked list. So let's save this. This is saved. Let's make a new. And we're going to format it as rich text. And we're going to come here to our text edit settings, do new document. If it is rich text, plain text font, we're going to change the rich text font to Courier New. Size 16. I guess we'll do 18. Okay. We're going to delete this so we can get a new one with our rich text settings. Format, make rich text. Cool. So, problem. Create a method that returns the middle node of a linked list. Using 2 pointers moving in parallel was a good solution to the previous problem. However, there are other problems where having 2 pointers moving in parallel wouldn't be as useful. Let's take a look at one of those problems and consider a new strategy that uses 2 pointers moving at different speeds. Consider the following problem. Create a method that returns the middle node of a linked list. For example, given the linked list with the following elements, 1 points to 2, points to 3, points to 4, points to 5, points to 6, points to 7, the middle node would be the element with the value 4. Approaches. As before, it's possible to find a solution by iterating through the entire list, creating a list representation, and then returning the middle index. But also as before, this can potentially take up lots of extra space. Create list. While the linked list has not been fully iterated through, push the current element onto list, move forward 1 node, return list length divided by 2. Instead, we can use 2 pointers to move through the linked list. The first pointer takes 2 steps through the linked list for every 1 step that the second takes. So, if we were to, as before, it's possible to find a solution by iterate. If you were to iterate through the entire list and create a list representation and then return the middle index, this could this doubles the space. Is it called space complexity? Yeah. Doubles the memory allocation and therefore has a space complexity of O of n. Instead, we can use 2 pointers to move through the linked list. And I just want to, if we were to iterate through the entire linked list and create a list representation. So we use 2 pointers to move through the linked list. The first pointer takes 2 steps through the linked list for every 1 step that the second takes. So it iterates twice as fast, and I'll add when the first pointer reaches the end of the list, the slower second pointer will be pointing to the middle element. So cool. And the pseudocode for this so fast pointer equals linked list head, slow pointer equals linked list head, while fast pointer is not none. Move fast pointer forward if the end of the linked list has not been reached. Move fast pointer forward. Move slow pointer forward. Oh, I see. Yeah, you're moving it twice for each time you move the slow pointer. Makes sense. And then this will end when the fast pointer is none. And so at that point we return slow pointer. Makes sense. So starting state, first and second are at 1. First tick, first has moved twice and slow has moved once. On the second tick, first moves 2 more times and slow moves 1 more time. And on the third tick, first moves 2 more times and slow moves 1 more time. On the final tick, the first will be at the end of the list and the slower one will be at the second one. The fast pointer will be at the end of the list and the slow pointer will be at the middle point in the list. As long as we always move the fast pointer first and check to see that it is not none before moving it, and the slow pointer again, we'll exit iteration at the proper time and have a reference to the middle node with the slow pointer. Implementation. Complete the find middle function and return the middle node of linked list. You can assume that the linked list has no cycles. So complete the find middle function, return the middle node of linked list. You can assume that the linked list has no cycles. Return the right weighted middle for even length linked lists. For example, in a linked list of 4 elements, it should return the element at the 3rd position. Use generate test linked list length to generate linked lists with values from 1 to 2 up to the length to test your function. For instance, generate test linked list 4 return results in 1 points to 2 points to 3 points to 4. So from linked list, import linked list. Complete this function, def find middle, linked list pass, and then we have our def generate test linked list length. Linked list equals a linked list for I in range length to 0, -1. So we get back a reverse list. Linked list dot insert beginning, return linked list, so we get a ascending linked list up to our length starting at 1. Use this to test your code. Test list equals generate test linked list 7. So this would be 1 points to 2, points to 3, points to 4, points to 5, points to 6, points to 7. So now that's our test list. Print the test list stringify list. So essentially just that. Middle node equals find middle test list, print middle node dot value. So how do we do this right? First, initialize a fast pointer and a slow pointer, both to the head of our linked list. So fast pointer equals linked list dot get head node, and slow pointer equals linked list dot get head node. And then what we want to do is while fast pointer is pointing to a node, while fast pointer move fast pointer to the next node. Fast pointer equals fast pointer dot get next node. If what? That. So while it's pointing to something, move it to the next node. I don't want to look at what I wrote. What's the if here? Damn it. If the end of the linked list, okay, has not been reached. So you check again. So while fast pointer, move fast pointer to the next node. Fast pointer equals fast pointer, get next node. If the end of the linked list has not been reached, so if fast pointer is not none, so if it's still not none, move the fast pointer again and move the next pointer once. Fast pointer equals fast pointer dot get next node, and slow pointer equals slow pointer dot get next node. And then once it's all said and done, the loop will end when fast pointer reaches the end of the linked list, and at that point the slow pointer will be at the middle element, so we can return the slow pointer. Nice. Solution and alternatives. In Python, we can implement the find middle function as such. So def find middle linked list, fast equals linked list dot head node, slow equals linked list dot head node. While fast equals fast dot get next node. If fast equals fast dot get next node, slow equals slow dot get next node, return slow. As with the nth to last solution, this solution has O of n time complexity and O of 1 space complexity. We always use two variables no matter what size the linked list is, 2 pointers. Half speed. Another equally valid solution is to move the fast pointer once with each loop iteration, but only move the slow pointer every other iteration. Okay. Conclusions. Many linked list problems can be solved with the two-pointer technique. If it seems like a linked list problem requires keeping track of multiple positions or creating other data representations, such as using a list, consider whether two pointers iterating in parallel or at different speeds could help solve the problem efficiently. We didn't cover full solutions to these here, but variations on the two-pointer technique can be used to detect a cycle in a linked list, rotate a linked list by k places. So let's write out our solution for this. I'm just going to go ahead and do it again. Python def what's the problem? Create a method, return the middle node, return the middle node of linked list, takes in a linked list. So we do fast pointer, which is linked list dot head node, slow pointer, which is linked list dot head node, while fast pointer, equals fast pointer dot get next node, and if fast pointer is is not none. Fast pointer equals fast pointer dot get next node, and slow pointer equals slow pointer dot get next node. And when all that's said and done, return slow pointer. And that's right? Just making sure. Yep. Yeah, we don't need to do that again actually. So if fast pointer. Yep. Cool. And this is middle node of a linked list. What I call the last one? I should call the nth last node of a linked list. I call this one middle node of a linked list. Satisfied? Are you? I'm very satisfied. I like this one. No, just leave me alone. A conceptual overview of doubly linked lists. So, hold on 1 second. I need to stretch. Okay, thank you for your patience. So, doubly linked list, a conceptual overview of doubly linked lists. Like a singly linked list, a doubly linked list is comprised of a series of nodes. Each node contains data and two links or pointers to the next and previous nodes in the list. The head node is the node at the beginning of the list, and the tail node is the node at the end of the list. The head node's previous pointer is set to null, and the tail node's next pointer is set to null. The head node's previous pointer is set to null, and the tail node's okay, yeah. Think of your daily commute on the subway as a real-world example of a doubly linked list. Your home is the head of the list, your place of work is the tail, and every stop in between is another node in the list. Doubly linked list example. So here we have node A, which has data A, and a previous node equal to null, and the next node equal to node B. Node B has data B, a previous node of node A, and a next node of node C, and node C has data C, a previous node of node B, and the next node of null. We could think about this as if we live at Times Square and our job is at 23rd Street, then stop equals Times Square, previous equals null, next equals Penn Station. Penn Station, stop is Penn Station, the previous is Times Square, and the next is 23rd Street, and 23rd Street, our stop is 23rd Street, the previous is Penn Station, and the next is equal to null. Adding to the list. In a doubly linked list, adding to the list is a little complicated, as we have to keep track of and set the node's previous pointer, as well as update the tail of the list if necessary. Adding to the head. When adding to the head of the doubly linked list, we first need to check if there is a current head to the list. If there isn't, then the list is empty, and we can simply make our new node both the head and tail of the list and set both pointers to null. If the list is not empty, so again, adding to the list. In a doubly linked list, adding to the list is a little complicated, as we have to keep track of and set the node's previous pointer, as well as update the tail of the list if necessary. Adding to the head. When adding to the head of the doubly linked list, we first need to check if there is a current head to the list. If there isn't, then the list is empty, and we can simply make our new node both the head and tail of the list and set both pointers to null. Again, if there isn't, then the list is empty, and we can simply make our new node both the head and tail of the list and set both pointers to null. If the list is not empty, then we will set the current head's previous pointer to our new head, set the new head's next pointer to the current head, and set the new head's previous pointer to null, adding to the tail. Similarly, there are two cases when adding a node to the tail of a doubly linked list. There are two cases when adding a node to the tail of a doubly linked list. Give me one sec. So, no. Let me get this on. Okay, cool. 1, 2, 1, 2. Adding to the tail. Similarly, there are two cases when adding a node to the tail of a doubly linked list. If the list is empty, then we make the new node the head and tail of the list and set the pointers to null. If the list is not empty, then we set the current tail's next pointer to the new tail, set the new tail's previous pointer to the current tail, set the new tail's next pointer to null. So adding to the head and tail, if we have an original list with node A has data A and a previous node null and a next node B, and node B has data B and a previous node of node A and a next node null. To add to the head, we create this node C and put data C, previous node is null, next node is node A, and we update node A with the previous node of node C. Whereas if we add to the tail, we still have node A as was before, we still have node B as was before, but now we created this node C with data C, we made node C's previous node B, and we made node B's next node C, and node C has a next node of null, removing from the list. Due to the extra pointer and tail property, removing the head from a doubly linked list is slightly more complicated than removing the head from a singly linked list. However, the previous pointer and tail property make it much simpler to remove the tail of the list, as we don't have to traverse the entire list to be able to do it. Removing the head. Removing the head involves updating the pointer at the beginning of the list. We will set the previous pointer of the new head, the element directly after the current head, to null, and update the head property of the list. If the head was also the tail removal process will occur as well. Removing the tail. Similarly, removing the tail involves updating the pointer at the end of the list. We will set the next pointer of the new tail, the element directly before the tail, to null, and update the tail property of the list. If the tail was also the head removal process will occur as well. So removing from the head and tail, the original list, node A with data A and a previous node of null, and a next node of node B. Node B has data B, previous node of node A, and the next node of node C. Node C has data C, previous node of node B, and the next node null. In order to remove the head, what we've done is we've gotten rid of node A. In order to do so efficiently, we need to make a previous node for node B. We need to make its previous node null, and its next node is still node C. And in order to remove the tail, we make node B's next node null, and we got rid of node C. Removing the middle, and just to read that again, right? So removing the head, Removing the head involves updating the pointer at the beginning of the list. We will set the previous pointer of the new head, the element directly after the current head, to null, and update the head property of the list. If the head was also the tail removal process will occur as well. And for removing the tail, similarly, removing the tail involves updating the pointer at the end of the list. We will set the next pointer of the new tail, the element directly before the tail, to null, and update the tail property of the list. If the tail was also the head removal process will occur as well. Removing the middle of the list. It is also possible to remove a node from the middle of the list. Since that node is neither the head nor the tail of the list, there are 2 pointers that must be updated. We must set the removed node's preceding node's next pointer to its following node. So again, removing from the middle of the list. It is also possible to remove a node from the middle of the list. Since that node is neither the head nor the tail of the list, there are 2 pointers that must be updated. We must set the removed node's preceding node's next pointer to its following node. We must set the removed node's following node's previous pointer to its preceding node. There is no need to change the pointers of the removed node, as updating the pointers of its neighboring nodes will remove it from the list. If no nodes in the list are pointing to it, the node is orphaned. So to remove from the middle of a list, if we have node A, node B, and node C, then what we need to do is make node A point to, or make node A's next node node C, and make node C's previous node node A. So now node B is orphaned, and we just have this linked list. Review. Let's take a minute to review what we've covered about doubly linked lists in this lesson. They are comprised of nodes that contain links to the next and previous nodes. They are bidirectional, meaning it can be traversed in both directions. They have a pointer to a single head node, which serves as the first node in the list. They have a pointer to a single tail node, which serves as the last node in the list. They require the pointers of the head of the list to be updated after addition to or removal of the head. They require the pointers of the head of the list to be updated after addition to or removal of the head. They require the pointers at the tail of the list to be updated after addition to or removal of the tail. They require the pointers of the surrounding nodes to be updated after removal from the middle of the list. Cool. Oh, word. So, node class and constructor. Now that we've learned about doubly linked lists, let's implement one in Python. As a reminder, a doubly linked list is a sequential chain of nodes, just like a singly linked list. The nodes we used for our singly linked lists contained 2 elements, a value, a link to the next node. The difference between a doubly linked list and a singly linked list is that in a doubly linked list, the nodes have pointers to the previous node as well as the next node. This means that the doubly linked list data structure has a tail property in addition to a head property, which allows for traversal in both directions. So the nodes we will use for our doubly linked list contain 3 elements: a value, a pointer to the previous node, a pointer to the next node. Depending on the end use of the doubly linked list, there are a variety of methods that we can define. That didn't feel like it sunk in properly, so I'm gonna read it again. As a reminder, a doubly linked list is a sequential chain of nodes, just like a singly linked list. The nodes we used for our singly linked lists contained 2 elements: a value, a link to the next node. The difference between a doubly linked list and a singly linked list is that in a doubly linked list, the nodes have pointers to the previous node as well as the next node. This means that the doubly linked list data structure has a tail property in addition to a head property, which allows for traversal in both directions. So, the nodes we will use for our doubly linked list contain 3 elements: a value, a pointer to the previous node, a pointer to the next node. Depending on the end use of the doubly linked list, there are a variety of methods that we can define. For our use, we want to be able to add a new node to the head beginning of the list, add a new node to the tail end of the list, remove a node from the head of the list, remove a node from the tail of the list, find and remove a specific node by its value, print out the nodes in the list in order from head to tail. To start, we are going to look at the updated node class and create the constructor. Ready? Let's go. Note, we will reuse the .stringify list method from our linked list class, but we're going to create the rest of the methods ourselves. We are going to use a provided node class, which you can find at the top of script.py. We've added a prev node property to the class, as well as .setPrev node and .getPrev node methods. Take a look to see the changes. So this class node, def init, self, value, next node equals none, previous node equals none, self.value equals value, self.next node equals next node, self.prev node equals prev node, def set next node, self next node, self.next node equals next node, def get next node, self, return self.next node, def set prev node, self prev node, self.prev node equals prev node, def get prev node, self, return self.prev node, def get value, self, return self.value. Cool. In our doubly linked list class at the bottom of script.py, create an init method constructor that only has self as a parameter, since each list will be empty when it's created. So our class doubly linked list, def dunder init, self. Inside your init method, create head node and tail node instance variables. The nodes have no value yet, so set them to none, then delete pass. Self.head node is none. Self.next node is none. Oh, sorry, tail node. Goodness. Tailo node. There. Before moving on, take a moment to think about doubly linked lists. What do you think are some possible real-life uses? Take a look at the hint for some answers. So I think the subway example was a very good example of a doubly linked list. I think that maybe if you're thinking about like a line of people, you could say, oh, that's just a linked list because you only care about who's next, but that's not the case. You also care about who's behind you in the line in case you want to do backsies. I would say another example of a doubly linked list where you need to keep track of what's ahead of you and what's behind you is like a race. So you see who's in the front of the race, but also who's in second place, who's in third. And when you're in a race, you're wondering, oh, how many people are in front of me? How many people are behind me? You're wondering about your place in the list. And let's see the hint. Some uses are a music player with next and previous buttons, makes sense. An app that shows you where your subway is on the train line, makes sense. The undo and redo functionality in a web browser, makes sense. Adding to the head. In a singly linked list, we can add to the head of the list by checking to see if it already has a head. We then either set the new node as the head if there was no head, or update the head property and link the past head to the new head. Since a doubly linked list has an additional tail property and is built with nodes that each have 2 pointers, there are a few more steps. Start by checking to see if there is a current head to the list. If there is, meaning the list is not empty, then we want to reset the pointers at the head of the list. Set the current head's previous node to the new head. Set the new head's next node to the current head. Update the head property to be the new head. Finally, if there isn't a current tail to the list, meaning the list was empty, update the tail property to be the new head, since that node will be both the head and tail of the list. I'm going to go ahead and read that again. Adding to the head. In a singly linked list, we can add to the head of the list by checking to see if it already has a head. We then either set the new node as the head if there was no head, or update the head property and link the past head to the new head. Since a doubly linked list has an additional tail property and is built with nodes that each have 2 pointers, there are a few more steps. Start by checking to see if there is a current head to the list. If there is, meaning the list is not empty, then we want to reset the pointers at the head of the list. Set the current head's previous node to the new head. Set the new head's next node to the current head. Update the head property to be the new head. Finally, if there isn't a current tail to the list, meaning the list was empty, update the tail property to be the new head, since that node will be both the head and tail of the list. So define an add to head method that takes self and new value as parameters. Inside, create a new head node that takes new value as a parameter, a current head node that's set to the list head. So within our class doubly linked list, def add to head, self, new value. Inside, create a new head node. So new head equals node new value, current head equals node that's set to the list head. You create a new variable named current head and set it to, oh, okay. Current head node, okay, got you. Don't need to make a new node for it. We just set it to the list head. If there is a current head to the list, set current head's previous node to new head. So if there was a current head to the list, so if current head dot set previous node to new head. So if current head dot set previous node to new head, set new head's next node to current head. New head dot set next node current head. Remember to use the node classes set prev node and set next node methods. Did you check if current head isn't equal to none? I thought I could do that with if current head. Hold on. Yes, there's a difference between these two lines in Python. If current head is not none, check specifically whether current head is not equal to none. It will be true if current head holds any value other than none, including 0, false, an empty list, curly braces, parentheses, and so on. If current head checks the truthiness of current head. It will be true if current head has a truthy value. Most values are truthy except for 0, false, and empty list. Okay. Curly braces, parentheses, empty string, and none, which are considered falsy. So the key difference is how they handle falsy values other than none. So again, if current head is not none, check specifically whether current head is not equal to none. It will be true if current head holds any value other than none. Whereas if current head checks the truthiness of current head, it will be true if current head has a truthy value. Okay, so it's really a specificity thing. But for the purposes of this, they want us to use current head is not none, which I guess makes sense. So outside the if statement, set the list head to new head. So self.head node equals new head. Lastly, if the list doesn't have a tail, set the list tail to the new head. If self.tail node is none, self.tail node equals new head. Adding to the tail. Since doubly linked lists have a tail property, we don't have to iterate through the entire list to add to the tail like we did with a singly linked list. The new method will mirror what we did in our add to head method. Start by checking to see if there is a current tail to the list. If there is, meaning the list is not empty, then we want to reset the pointers at the tail of the list. Set the current tail's next node to the new tail. Set the new tail's previous node to the current tail. Update the tail property to be the new tail. Finally, if there isn't a current head to the list, meaning the list was empty, update the head property to be the new tail, since that node will be both the head and tail. Again, start by checking to see if there is a current tail to the list. If there is, meaning the list is not empty, then we want to reset the pointers at the tail of the list. Set the current tail's next node to the new tail. Set the current tail's next node to the new tail. Set the new tail's previous node to the current tail. Update the tail property to be the new tail. Finally, if there isn't a current head to the list, meaning the list was empty, update the head property to be the new tail, since that node will be both the head and tail. So, define an add to tail method. That takes self and new value as parameters. Inside, create a new tail node. That takes a new value as a parameter. A current tail node that's set to the list tail. If there is a current tail to the list, set the current tail's next node to new tail. Set new tail's previous node to the current tail. Outside your if statement, set the list tail to the new tail. Lastly, if the list doesn't have a head, set the list head to the new tail. Nice. Removing the head. Due to the added tail property, removing the head of the list in a doubly linked list is a little more complicated than doing so in a singly linked list. Start by checking if there is a current head to the list. So actually, give me 1 second before I get into this. We good. Hold up. One, two, 1, 2. Cool. So, removing the head. Due to the added tail property, removing the head of the list in a doubly linked list is a little more complicated than doing so in a singly linked list. Start by checking if there's a current head to the list. If there isn't, the list is empty. So, there's nothing to remove and the method ends. Otherwise, update the list head to be the current head's next node. Otherwise, update the list head to be the current head's next node. If the updated head is not none, meaning the list had more than one element when we started, set the head's previous node. Hold on, I need to restart. So, due to the added tail property, removing the head of the list in a doubly linked list is a little more complicated than doing so in a singly linked list. Start by checking if there's a current head to the list. If there isn't, the list is empty, so there's nothing to remove and the method ends. Otherwise, update the list head to be the current head's next node. If the updated head is not none, meaning the list had more than one element when we started, set the head's previous node to none, since there should be no node before the head of the list. If the removed head was also the tail of the list, meaning there was only one element in the list, call .removeTail to make the necessary changes to the tail of the list. We will create this method in the next exercise. Finally, return the removed head's value. Define a remove head method that only takes self as a parameter. Move head self. Inside, create a removed head variable and set it to the list head node. Check if removed head has no value. If so, that means there's nothing to remove, so return none to end the method. Outside of your if, set the list head to removed head's next node. Self dot head node removed head dot get next node. You set self head's node previous node to none. Outside of your if, set the list head to remove head's next node. Self dot head node equals remove head next node. Oh, so what I did was fine. It's just that I forgot to read the next line. If the list still has a head, set its previous node to none. If self.head node is not none, self dot head node dot set prev node none. Since the head of the list should have previous node, check if removed head is equal to the list tail. If so, call the remove tail method. We will create this in the next exercise. So check if removed head is equal. So if removed head is equal to self dot tail node, call the remove tail method. So if removed head is equal to self.tail node, do we do self dot remove tail? Finally, return removed head's value. Oh. Return remove head dot get value. Removing the tail. The doubly linked list tail property allows us to remove the tail just as easily as we could remove the head. In fact, like with the .add to head and .add to tail methods, the .remove tail method will closely mirror the .remove head method. Start by checking if there's a current tail to the list. If there isn't, the list is empty, so there's nothing to remove and the method ends. Otherwise, update the list tail to be the current tail's previous node. If the updated tail is not none, meaning the list had more than one element when we started, set the tails. So again, removing the tail. The doubly linked list's tail property allows us to remove the tail just as easily as we could remove the head. In fact, like with the .add to head and .add to tail methods, the .remove tail method will closely mirror the .remove head method. Start by checking if there's a current tail to the list. Start by checking if there's a current tail to the list. If there isn't, the list is empty, so there's nothing to remove, and the method ends. Otherwise, update the list tail to be the current tail's previous node. So update the list. So list has a tail. Update the list tail to be the current tail's previous node. So start by checking if there's a current tail. So there is a current tail to the list. Now what we're going to do is we're going to update the list tail to be the current tail's previous node. I see. If the updated tail is not none, meaning the list had more than one element when we started, set the tail's next node to none, since there should be no node after the tail of the list. If the removed tail was also the head of the list, meaning there was only one element in the list, call .remove head to make the necessary changes to the head of the list. Finally, return the old tail's data. So we're going to define a remove tail method. Takes the self. Inside, create a remove tail variable and set it to the list's tail. Check if removed tail has no value. If so, that means the list is empty and there's nothing to remove, so return none to the end to end the method. Return none. Outside of your if, set the list tail to remove tail's previous node. Outside of your if, set the list's tail, so self dot tail node. Set the list tail to remove tail's previous node. Remove removed tail dot get prev node. If the list still has a tail, meaning that the list isn't now empty, so if self dot tail node is not none, set the tail's next node to none. self dot tail node dot set next node none. Since the tail of the list shouldn't have a next node, check if removed tail is equal to the list head. Check if removed tail is equal to self.head node. If so, call the remove head method. If remove tail is equal to self.head node, self.remove head. Finally, return the remove tail's value. Cool. Removing by value 1. In addition to removing the head and the tail of the list, it would also be useful to be able to remove a specific element from anywhere in the list. Imagine that you have a list of errands to run. You don't always do your errands in order, so when you finish doing your laundry and want to cross it off, that could be somewhere in the middle of the list. We are going to build a .remove by value method that will allow you to cross off, remove that errand, no matter where it is in the list. In order to do this, iterate through the list to find the matching node. If there is no matching element in the list, return none. If there is a matching node, we will then check to see if it is the head or tail of the list. If so, call the corresponding .remove head or .remove tail method. If not, that means the node was somewhere in the middle of the list. In that case, remove it by resetting the pointers of its previous and next nodes. Finally, return the node's value property, right? Define a remove by value method. That takes self and value to remove as parameters. Inside it, create a variable called node to remove. We don't know what it is yet, so set it to none. Create a current node variable. And set it equal to the list head. Then create a while loop. That runs while current node is in none. So while current node is not none. Inside the loop, update the current node to be its next node. This is how we will iterate through the list as we look for the matching node. If you accidentally create an infinite loop and your code won't stop running, you can reload the page to stop it. Inside the while loop, but before you updated current node to be its next node, create an if statement that checks if current node's value matches the passed in value to remove. If it does, that means we have found the matching node. Inside the if, set node to remove to current node. Break to leave the while loop, since we don't need to keep looking through the list. Outside your while loop, check if node to remove has any value. If it doesn't, that means there was no matching node in the list, so return none to end the method. Did you check if node to remove is equal to none? Sorry. Outside your while loop, check if node to remove has any value. If it doesn't, that means there was no matching node in the list, so return node to end the method. So again, to understand what's happening here, we define this method remove by value that takes in self and takes in a value to remove. We create this node to remove variable and set it equal to none. We create a current node variable and set it equal to the self.head node. While current node is not none, if current node dot get value is equal to the value to remove, node to remove equals current node and break out of the loop. Otherwise, current node equals current node dot get next node, and that's going to keep looping until current node is none. If node to remove is none, return none. That would mean that there was no matching node in the list. Removing by value 2. Now that we've found the node that we want to remove from the list, or returned none if it doesn't exist, it's time to actually remove the node. This means resetting the pointers around the node. There are 3 cases here. The node was the head of the list, in which case we can just call remove head. The node was the tail of the list, in which case we can just call remove tail. The node was somewhere in the middle of the list, in which case we will need to manually change the pointers for its previous and next nodes. Still in your remove by value method, check if node to remove is the list head. If so, call remove head. If node to remove is equal to self.head node, self.remove head. Else, if node to remove is the list tail, call remove tail. Else, elif node to remove is equal to self.tail node, self.remove tail. Else, we know that the node is somewhere in the middle of the list. To remove it, we will need to reset the pointers for the nodes around it in an else block. Create a next node that is equal to node to remove's next node. So next node equals node to remove dot get next node, a prev node equals node to remove dot get prev node. Now that we have our nodes, we can remove the pointers to and from node to remove, and have next node and prev node point to each other, still in the else block. Set next node's previous node to prev node. Next node dot set prev node prev node, and set prev node's next node to next node. Prev node dot set next node to next node. Finally, outside of the else block, return node to remove. Return node to remove. Using the list, you finished your doubly linked list class. Now we're going to use that class to model a subway line. A doubly linked list is a great data structure to use to model a subway, as both have a first and last element and are comprised of nodes or stops with links to the elements before and after them. We will add to and remove stops from our subway line and print it out to see what we've done. The stringify list method is the same as the one from the linked list class and has been provided for you. We're going to model a fictional subway line that will travel from Central Park to the Brooklyn Bridge. At the bottom of script.py, outside the doubly linked list class, create a new doubly linked list named subway. So subway equals doubly linked list. The subway starts at Central Park and winds its way downtown. In the following order, add Times Square to the head of the list. So subway dot set head node. Is that it, right? Double linked list. Self head node is none. So add to head. Self new value. So subway add to head Times Square. Subway dot add to head Grand Central. Subway dot add to head Central Park. And then print the list. Print subway. Subway.stringify list. Stringify list. Central Park, Grand Central, Times Square. The subway continues from Times Square down to the Brooklyn Bridge. In the following order, add Penn Station to the tail of the list. So subway.add to tail Penn Station. Subway.add to tail Wall Street. Subway.add to tail Brooklyn Bridge. And print the list again. Nice. Oh no, there's a construction happening on the subway line. The Central Park and Brooklyn Bridge stops will temporarily be closed. Remove them from your list without iterating through the entire list, then print the list again. Subway.remove by value. The Central Park and Brooklyn Bridge stops will temporarily be closed. Central Park subway.remove by value. Brooklyn Bridge. Print the list again. Did you remove the head of the list? Central Park, Brooklyn Bridge. I thought so. Hold on. Okay, so it wanted me to use the remove. Okay, so subway dot remove head, right? Yeah. Remove head. Central Park. Subway dot remove tail. Brooklyn Bridge. Oh, I gotta print the list. Oh, yeah, I don't even have to add anything. It turns out the Times Square station is under construction as well. Remove it from the list. And then print the list for the last time. Review. Congratulations, you have created a doubly linked list class in Python. We did this by using our node class to hold the value and links between nodes, implementing a doubly linked list class to handle external operations on the list, like adding and removing nodes, creating an instance of our list, and using the stringify list method to track the changes we made. Feel free to play around a bit with your code. Here are some ideas. Create a few nodes and add them to both ends of a new doubly linked list. Remove your doubly linked list's head or tail node. So first of all, create a few nodes and add them to both ends of a new doubly linked list. That's easy to do. I don't want to do that. Remove your doubly linked list head or tail node. I mean, this is all just calling the methods. Print your list again with the nodes removed. Remove a specific node from somewhere in the middle of the list. Then print the list again. Did it work? We created our remove by value method by iterating from the head of the list to the tail. Do you think you could start at the tail and iterate backward? We created our remove by value method by iterating from the head of the list to the tail. Do you think you could start at the tail and iterate backward? Try it. That seems interesting. How much time do I have? Just over an hour, and all that's left in doubly linked list is a quiz. So yeah, let me try to rewrite the remove by value. So we'll do def remove by value by iterating from the head of the list to rev self value to remove. So node to remove is none. Current node self dot head. So current node equals self dot tail node, while current node is not equal to none if current node dot get value is equal to value to remove. Node to remove equals current node break. So if current node dot get value is equal to the value to remove, node to remove equals current node break. Current node equals current node dot get previous node. It's removing backwards through it. If node to remove is equal to none, return none. If node to remove is equal to self dot head node. So if node to remove is equal to self dot head node, self dot remove head. Sorry. Yeah. This stands. Else if, but put these backwards. If node to remove is equal to self dot tail node, move self dot tail. Else if node to remove is equal to self dot head node, self dot remove head. Else next node equals node to remove dot get next node. Previous node equals node to remove. So previous node equals node to remove dot get previous node. Next node is node to remove dot get next node. Previous node dot set previous node dot set next node. Well, I'm getting confused here. Else previous node is so else previous node. So it's previous node equals node to remove dot get previous node, and next node equals node to remove dot get next node. Previous node dot set next node is next node. Yeah, that makes sense. and next node dot set previous node is previous node. Return node to remove. Let's test it out. So if I have a list 1 equals doubly linked list, and I do list 1 dot set add to head, and then I do print this one dot stringify list C321, and if I do list 1 dot remove by value rev, two, and I move this print statement down to the bottom. Cool, it worked. The add to head and add to tail methods in doubly linked list are the same as those in the linked list. The add to head and add to tail methods in doubly linked list are the same as those in linked list. False. Yes, they are different because of the added tail node property in doubly linked list. What would you add to complete the following add to tail method? So def add to tail self new value, new tail equals node new value, current tail equals self dot tail node. So new tail is this node with this new value. Current tail, we're setting that to self dot tail node. If current tail is not equal to none, current tail dot set next node new tail dot set previous node current tail. So current tail dot set next node new tail dot set previous node current tail. You got it. Given the following code, how would you complete the remove by value method? Def remove by value, self value to remove, node to remove equals none, current node equals self dot head node. While current node is not equal to none, if current node dot get value is equal to the value to remove, node to remove equals current node and break. Current node equals, so otherwise current node equals current node dot get next node. And we're going to keep doing that until current node's value is equal to the value to remove. If node to remove is equal to none, return none. If node to remove is equal to self.head node, self.remove head. Else if node to remove is equal to self.tail node, self.remove tail. Else next node equals node to remove dot next node. Get next node. Previous node equals node to remove dot get previous node. And next node dot set previous node is previous node, and previous node dot set next node is next node. So else next node equals node to remove dot get next node, previous node equals node to remove dot get previous node, next node dot set previous node is previous node, and previous node dot set next node is next node. What would you add to complete the following dot remove tail method? Def remove tail self removed tail equals self dot tail node. If remove tail So wait. What would you add to complete the following remove tail method? Def remove tail takes in self. Remove tail equals self.tail node. If remove tail is not equal to none, return none. Or sorry. If remove tail is equal to none, return none. Self.tail node equals remove tail dot get previous node. If self.tail node is not equal to none, self.tail node dot set next node none. So we just set self.tail node to removed tail, it's previous node. So self.tail node equals remove tails. So remove tail is the self.tail node. Turn this around. Self.tail node is remove tail's previous node. If something is not equal to none, then self.tail node dot set next node to none. If remove tail is equal to self.head node, so what we should do, we want to make sure that self.tail node dot set next node to none. So we do if remove tail is not equal to none, yeah. Damn it. Whatever. What would you add to complete the dot remove head method? Def remove head self, removed head equals self dot head node. Remove head self, removed head equals self dot head node. If removed head is equal to none, return none. Break. Sorry, no. This indentation seems odd. If removed head is equal to none, return none. So we have this remove head method, right? Which takes in self, which is the list. First, we start by taking the list head node and assigning that to this removed head variable. Now, if this removed head variable is equal to none, we have no list, an empty list, whatever you want to call it, and return none. Otherwise, do we do self.tail node? No. Do we do self.head node equals removed head dot get next node? Probably. Do we do self.head node dot set previous node to none? No, because it would already be that. So it's definitely got to be this one. So if removed head is equal to none, return none. Self.head node equals removed head dot get next node. If self.head node is not equal to none, self.head node I can't think right now. What would you add to complete the remove head method? Def remove head self. Removed head equals self.head node. If removed head is equal to none, return none. Self.head node equals remove. First of all, let me clear this off. So, okay, let's try from the bottom up, right? If removed head is equal to something, then do something, return removed head dot get value. So if self.head node is not equal, okay, let's think about this, right? Let's say we have a W linked list 1, 2, 3. We start by assigning removed head to self.head node, which is in this case is 1. Now, if the removed head is none, then return none. That's not the case here. What do we do next? We want to remove the head. Do we do self.tail node on its own? No, that doesn't make sense. It's either going to be self.head node equals removed head node dot get next node, or self.head node dot set previous node to none. In this case, would self.head node dot set previous node to none make sense? It doesn't seem like it to me, because if self.head node is 1 its previous node is already none. Whereas if we do self.head node equals removed head dot get next node, that makes sense to me. So now we're setting the head node to 2. If self.head node is not equal to none, so if self.head node, so 2 is not equal to none, then what we'd like to do is self.head node dot set previous node to none. Now if removed head is equal to self.tail node, then we can just do self.remove tail, and then we return removed head dot get value. Which of the following is not true about the Python implementation of a doubly linked list? Which of the following is not true about the Python implementation of a doubly linked list? Nodes are no longer in one order since the list has a tail. There is an added dot remove by value method. Well, which one's not true? I could see already. Doubly linked list uses a different node class. That's not true. Doubly linked list does use. Oh, you're right. Nodes are no longer in one order since the list has a tail. I should have known that one. Consider the doubly linked list. A is pointing to B, which is pointing back to A, and B is pointing to C, which is pointing back to B. When removing node A, the pointers of which nodes should be updated. So when I remove node A, I just have to remove the pointer of node B. 2A. What is the difference between the doubly linked list and linked list constructors? The doubly linked list constructor has an added previous node pointer. The doubly linked list has an added tail node property. There are no differences. The constructors are the same. The doubly linked list constructor takes a parameter, while the linked list constructor does not. So it's this one. Given a fully functioning doubly linked list class, what will the following code output? So test list equals a doubly linked list. Test list add, so let's break out the, I can do it in my head. Test list add to head 9, so 9 is at the head. Test list dot remove tail, so now it's an empty list. Test list dot add to tail 8, so now it's 8. Test list dot add to tail 2, so now it's 8 2. Test list dot remove head, so now it's 2. Test list dot add to tail 4, so now it's 2 4. Test list dot remove by value 9, so that does nothing, so it's still 2 4. Test list dot remove head removes the 2, so it's 4. Print test list dot head node dot get value 4. What would you add to complete the following dot add to head method? Def add to head self new value. New head equals node new value. Current head equals self dot head node. If current head is not equal to none, current head dot set previous node to new head. New head dot set next node to current head. Something. So we're assigning new head to self dot head node. If self dot something is equal to none, then something equals new head. So if self dot tail node is equal to none, if self dot tail node is equal to none, self dot tail node equals new head. Doubly linked lists have all of the following except a tail. That's wrong. Nodes with 2 pointers. It's also wrong. A head. It's wrong. A direction. It's true. Doubly linked lists are bidirectional. 81. Not bad, not terrible. So next up is queues, which is definitely a topic that will be very, very fun to get into. But for now, I've gotta run. So peace. I'm out. You will not be able to reconnect your stream. We'll stop and you will no longer